It was surprising to many that I believe you chose a stainless steel for the vehicle. I could be wrong, but what were the technical and engineering reasons for that?
Sure. That's I think a very interesting question, because to a lot of people intuitively they would think of steel as being heavy, and rockets need to be light. So, well, that seems a pretty odd choice, picking a heavy sounding thing for rockets, especially orbital rockets that need to be very light. Intuitively, if you ask people who understand materials, they will say we want to make something incredibly light. They'll say probably you want to use state-of-the-art carbon fiber composite. That's usually what they'll say. And that's what we started out with, which was really a very advanced carbon fiber. Actually, it was only made in very small quantities. It cost $130 per kilogram, so it was very expensive material. And there are some challenges if you want to make the primary structure out of carbon fiber, which is that you've got to contain cryogenic fluid, and you need pressurization gas to pressurize the propellants in the main tanks and feed the engine turbopumps with a given inlet pressure. So if you have a carbon fiber tank, because it tends to be porous and also potentially flammable when subject to warm gaseous pure oxygen, because our vehicle is autogenously pressurized. So the oxygen tank is pressurized with gaseous oxygen, and the fuel tank is pressurized with gaseous methane. The resin and the carbon in the carbon fiber is potentially flammable with hot, pure oxygen gas. So you'd have to have some kind of liner. So when you look at the full mass and complexity of a carbon fiber system, you start having things that reduce the mass efficiency of carbon fiber, such as having an inert liner and being worried about gas permeating through the carbon fiber and that kind of thing. So but it still would be it's still an okay choice. However, we were having a lot of trouble making progress with the carbon fiber because this is a 9-meter diameter rocket. And so you're wrapping carbon fiber with typically, in this case, 60 to 120 plies, depending upon where you are in the tank. And you have to get all of those wrappings accurate and not leave bubbles or separator sheets or all the things that typically happen, or you've got to scrap the whole thing. And then you've got to get good mass properties, put it in an autoclave and put it under a lot of pressure. And then you need a gigantic autoclave because it's a 9-meter diameter with a 70-meter long boost stage. So this is autoclave from hell. And we just weren't making rapid progress with this material. So the other two materials worth considering are a high strength form of aluminum or potentially steel. So for Falcon 9, we use aluminum lithium, which is the highest strength to weight aluminum alloy that you can use. But the problem is it's very difficult to weld. You need to do friction stir welding, and also the material cost is quite high, arguably on the sort of $40 a kilogram level. But then there's the steel. The interesting thing about 300 series stainless steel is that its properties at cryogenic temperatures, its strength properties increase dramatically. So if you were to look at the material properties at room temperature, you'd be like, oh, it's not that great. But now go look at the temperature properties at liquid oxygen temperature. Oh, actually much stronger. Also no meaningful increase in brittleness. So it still has high toughness at cryogenic temperatures. It is much stronger, depending on how cold you go, up to twice as strong. And then if you can also cold work it. So you get if you go sort of full hard cold work and do the final bit of cold work at cryogenic temperatures, you get outstanding strength properties, which are roughly equal to an advanced carbon fiber. And this is, and in our case for Starship, both the fuel and the oxygen are cryogenic, so this helps a lot. Whereas for Falcon 9, you use cryogenic oxygen, but kind of room temperature kerosene fuel. So anyway, so we're both, this is quite a long explanation, hopefully interesting. If both fuel and oxygen are, fuel and oxidizer are cryogenic, now you get the strength properties in the primary structure of both tanks. So both are very strong, very tough and resilient, also very easy to weld stainless steel. And we started off with stainless steel 301. That did have some fracture toughness issues at cryogenic temperatures. We switched to 304, and now we developed our own alloy, which is Acero A30X, which is better than either 301 or 304. Now, stainless steel only costs about $4 a kilogram. So we went from $130 a kilogram advanced carbon fiber to $4 a kilogram stainless steel, from 120 plies to 1 ply. It's just coil from the mill, and basically the same strength, and very high toughness and resilience. And don't even need to paint it, which is great. So paint on a big vehicle weighs many tons, and it's quite difficult to paint big things. So but now there's another advantage. So obviously you can tell I'm a huge fan of stainless steel. Stainless steel and I should get a room or something. In making the vehicle reusable, so now it's coming in very hot. So the ship is coming in at hypersonic velocities, coming, sort of kind of like a Mach 25 entry velocity. So this would just obviously just melt it. But if you've got steel, your melting point is much better, higher than aluminum, and you can handle much better temperatures than carbon fiber, because the resin tends to have problems. Anything much above, say, 200 Celsius, or for carbon fiber or aluminum, is you start falling off a cliff from a strength standpoint. But for steel, you go 800, and it's fine. Even 1,000 can be fine. So for the ship, this means that the heat shield mass is significantly reduced, because the heat shield mass is determined by the temperature on the back of the tile that then transmits to the hull. So if the hull is steel, you can have thin heat shield tiles, whereas if the hull is carbon fiber or aluminum, you have to have thick heat shield tiles. And you also need no heat shielding at all on the leeward side of the ship. So it is actually lighter than the most advanced carbon fiber vehicle.
Yeah, I'm very surprised at that, but that was very, very interesting. I thought that the steel substituting for aluminum on reentry made some sort of sense. I didn't realize any of the other stuff.
Yeah, it's the cost is ridiculously low. It's like $4 a kilogram. Even for the special alloy that we're developing, although it requires like a mill run, it's not using anything super exotic. We might throw a little exotic, spicy something in there, but it's a small. It's it's going to be like 0.2%. So it's still going to be like maybe $4 a kilogram, maybe $4.50, and then it's just very easy to weld. Yeah, I love it. It's easy to repair. It's, if you want to add a sort of something to carry some wiring or plumbing or whatever, you just weld it right on. It's super easy. It's great.
Thank you.